doing? Okay, so we have this definition. We've seen this definition of the Laplace transform, that the Laplace transform of a function f, it's this integral, the integral of e to the minus st times f of t dt. And this thing is a function of s, a function of this new variable s. Okay. Okay, so it's a function of a new variable. We've introduced a new variable into the proceedings. So this integral no longer depends on t. Okay, it's independent of t because we're taking account of all the values of t from 0 to infinity. We're integrating it out. Okay. So this integral has various different values depending on what value of s you plug in. Now, as I said the last time, and we talked about the example of the logarithms, how logarithms simplify the evaluation of products and powers. They turn them into sums and products, respectively. Well, in a similar way, the Laplace transform is going to be a thing that enables us to solve differential equations. Okay? The differential equations are kind of too unsolvable or too intractable as they stand. But the Laplace transform transforms them into something new, which is a lot simpler structure, and that we can solve the transform problem and then transform it back. Okay, so we'll see all that process in detail when we meet it exactly. But for now, we just got that image in our minds of that idea. The transform being something which transforms the original ODE into a new kind of equation, which has got simpler structure, which you can solve. And then you do an inverse transform at the end to bring the solution of the transform problem back to the solution of the original ordinary differential equation. Okay, so some dead interesting conversations there, obviously, but thank you. But before we get to actually see some differential equations and see how the method works in detail, we just need to build up a bit more knowledge about the transform. Look at the transforms of some functions and see a few of its properties. A few of the necessary properties of the transform, which we'll need to show or explain how the method works for solving the differential equation. Okay. So last time we saw a couple of these examples. I just want to say a little bit more about the treatment of the existence of the transform. So a little bit more about the existence of the transform. Now, what do I say when I mean the existence of it? Well, the existence of it, I mean the question of, does this integral exist or not as a finite quantity? Does this integral converge or not? Because it's an integral over an infinite range, so it might not converge. It might not give you a finite answer. So actually, the variable s, the new variable s, is a complex variable. It's complex. So you can write it as its real and imaginary parts. I mentioned before, actually this nature of the variable s won't be that important for us because we're going to focus on using the Laplace transform as a tool for solving the differential equation. The fact that s is this complex variable sitting there at the end of the day won't be that crucially important for us. But I just do want to show a little bit about what conditions we need on S for the integral to exist. So last time we saw this first example, and I just want to look at it again, the example of the constant function 1, i.e. for all t greater than or equal to 0, f of t equals 1. Just an example of a constant function. Well, we saw last time how the Laplace transform of 1, you could say, is this integral from 0 to infinity e to the minus st dt. Okay, so normally you multiply by the function f of t inside the integral, but of course f of t is just the constant 1 here, so it's just the integral of e to the minus st. So this we saw was e to the minus st over minus s, and you're evaluating that at t equals 0 and, well, t equals to infinity, or really what you're saying is taking the limit as t tends to infinity. So the integral is just the integral of the exponential, so it's just the same exponential, and you're compensating for the fact that there's a minus s factor multiplying the t, so you have to divide by minus s as well. So if you think about differentiating this with respect to t, you get back to e to the minus st. So this becomes the limit as t goes to infinity of e to the minus st minus the evaluation at t equals 0. Well, when t is 0, you have e to the 0 in the numerator, which is just 1, e to the power 0. So it's minus 1 over minus s, so really it's plus 1 over s. So does this exist or not? Does this expression I've written down here as the transform for the function 1, is it valid? Well, there's nothing wrong with 1 over s as long as s isn't the number 0. But it's really about this limit. Does this limit exist or not? Okay. So the existence of the Laplace transform of 1 is really, the question of whether it exists or not is really the existence of this limit. So can we examine when that limit exists? Well, we use the fact that s is a complex variable, so we can name its real and imaginary parts. So we'll replace s by its expression as, its normal Cartesian form of a complex number, a real part plus an imaginary part. So we're taking the limit of this exponential. And now, well, an exponential like this, you can split apart as a product of the two exponentials. So the question that's in our minds as we're developing this is, does this exist? When does this limit exist? Okay. Now you've got it as a real exponential here, e to the minus at. A and b, remember, are real numbers. They're the real and imaginary part, respectively, of the complex number s. So you've got this real exponential, and then you also have this exponential e to the minus ibt. Now what happens to e to the minus ibt as t gets larger and larger? Anybody draw with their finger what happens to it as t gets larger and larger? So you drew this. Is that correct? What's it look like with your finger instead? You're doing some weird thing there. That doesn't look right either. It's a pretty simple motion with the finger that describes what happens to e to the minus ibt as t gets large. And isn't anything rude before you start trying. Do it with your finger. It's a circle, yeah. Remember, e to the I anything, that should remind you of complex numbers, the polar form of a complex number. E to the I times anything is a point on the unit circle in the complex plane. So as t gets larger and larger, e to the minus I bt, well, it's still e to the I something. So it just travels round and round the circle, round and round the unit circle in the complex plane. So if it was just this factor on its own, it's certainly not converging, okay? Because you've just got this point orbiting around on the unit circle as t gets larger and larger. You just keep going around. Every time t goes through a multiple of 2 pi or whatever, you know, you're back around the circle again. So, but it isn't just that bit, where it's multiplied by this factor, e to the minus at. But what does multiplying, so you've got your number on the unit circle in the complex plane. When you multiply it by a real number, that just scales it out or in. Yeah? When you've got a point on the unit circle in the complex plane, so e to the minus ibt lives here somewhere, the unit circle, and it just goes round and round in that direction perhaps, or maybe the other direction, I'm not sure. But it just goes round and round. When you hit it with a real number here, well, that just changes the radius of the circle. So what's the only way that it can converge? What's the only possible convergent answer I could put down on the right-hand side of this equation? And when does it happen? Yeah, so the only way you can have, so that's good, so 0. The only way you can have something which is legging it round a circle, the only way that that can actually be convergent is if actually the circle has 0 radius, so it's just a fixed point. Very good. And when does that happen, if and only if? No, t is going to infinity. That's not up for debate. The question is about a. If and only if. No, if a is 0, this is always 1. And so you've just got the point on the unit circle going round and round, not converging. No? Because if a was a negative number, then you'd have e to the positive t. But e to the positive t, as t gets large, that's going to go just fine, good. When a is greater than 0. If a is greater than 0, then this part, the e to the minus at part, that converges to 0 as t gets larger. Because you're taking the exponential of a negative number with larger and larger absolute value. Since e to the minus at is going to 0 if a is greater than 0. It's going to 0 as t goes to infinity. Otherwise, if a is not bigger than 0, if it's equal to 0, the point stays on the unit circle and doesn't converge because it just goes round and round. If a is less than 0, then actually you're making the circle have a bigger radius. So you got this point going round and round, ever further and further away from the origin. So it's certainly not converging. That's very good. The only way we can get an answer out of this is if a is bigger than 0, i.e. if the real part, what is a? Remember, a is the real part of the complex variable s. So the upshot is we get this answer that the Laplace transform of the constant function 1 is equal to 1 over s, and that this is valid for the real part of the variable s being strictly positive. That's good. That's the answer. That's the stuff I wanted to show you. but that there is some subtlety about whether or not, it's all very well and good writing down a definition saying here's what the Laplace transform is, and it's a function of a new variable s. But because it's an integral over an infinite range, there's this question of, does that integral make sense? Does it give you any kind of a sensible thing? Well, it does in certain circumstances. And they're not, they're just for any complex number. So that's any complex number in the right-hand half of the complex plane. Any complex number where the real part is bigger than 0. It doesn't matter about the imaginary part. Okay, that's just going to send this point round and round the circle in some way, but you're eventually just going to squash it down to the origin. And so that means that when we wrote down the answer to the integral, this first bracket is going to 0. It goes to 0 now whenever the real part of s is bigger than 0. And if the real part of s is not bigger than 0, this is not convergent. So we don't have an actual function value to talk about. The thing is divergent. The other example we looked at, second example, was the function defined by for every t bigger than 0, f of t was t. So that was this example here. But yeah, you see in this example, the same integral comes out. You're still, here, the Laplace transform of t, existence of this, again depends on exactly the same integral. Integral 0 to infinity e to the minus st dt. So it's only valid for real part of s bigger than 0 again. Okay, so you get the same condition. So we get this answer that the Laplace transform of the function t is 1 over s squared, and that's valid for the real part of s bigger than 0. Otherwise there isn't a transform. The third example, which I didn't go through last time, but it's just a three-liner really, is this case where you're dealing with the function f of t, where f of t is itself an exponential, and I'll write it as e to the minus at, so it's just some exponential, e to the minus at, but a could be positive or negative, so this could be any exponential really. And well, here you see, what integral does it depend on? It depends on this integral, e to the minus of s plus a times t. So that integral is only going to converge if the real part of the thing in the bracket is, if its real part is greater than 0. So we do get this answer out here, but it's only valid for the real part of s minus a bigger than 0. Now, if a is a real number, the real part of s minus a is equal to the real part of s minus a, because a is already real. So that's true if and only if the real part of s is bigger than that quantity a. So it's a slightly different convergence condition on s, but it's still pretty much half a complex plane's worth. Okay, it's just the dividing line isn't the imaginary axis now. It's just some other vertical axis located at the value a. And for every number which is to the right of that in the complex plane, then the Laplace transform exists, and it's continuous. The Laplace transform exists because the integral is convergent. So for any Laplace transform, there is an associated convergence condition on S. There's an associated convergence condition on the variable S. Now, you know, after this point in time, we mightn't refer too much to them again, but it's important to realize that they are there. But I think they all really, well, I better be careful what I say, but I think they pretty much always exist for the real part of the variable S bigger than some numbers. So even if you've got a bunch of these conditions to apply together, there'll be some region of the complex plane where all the conditions are satisfied. So there'll be some region of the complex plane for which the transform will exist. Okay. So, you know, we won't trouble ourselves every time we look at a Laplace transform of wondering, does this exist or not? We'll just assume that for certain values of the complex variable S, it will exist. So we'll be able to just get on with using its existence to solve the differential equations. And in practice, when we do come to solving the differential equations, we won't always be insisting that we evaluate the Laplace transforms using the definition. Okay. Remember the log tables I showed you the other day? You know, the tables of numbers. And this is our similar thing for our functions. So there's a couple of pages here which is lifted directly off the formula handbook that you have with you in exams and that. So there's a couple of pages here showing standard functions down the left-hand side and their corresponding Laplace transforms down the right-hand side. And then on the second page, there's a few functions at the top, but then we get more onto properties, general properties that the Laplace transform has. And it's those that we're going to get onto starting to discuss later on this afternoon. But I just thought I'd show you maybe one or two more of these standard ones. Well, we've done the first two, the function 1, the function t. We've done the exponential one, e to the minus at. Okay, we still haven't dealt with t to the power n. You could think of t to the power n here. We've seen the t to the, when we did the function t, we had to use integration by parts. We had to integrate t times the exponential. So we did integration by parts to get that out. To do t to the power n times the exponential, you just have to do repeated applications of integration by parts. So you just have to iterate the integration by parts n times, and then you'll get the answer out for the transform of t to the power n. Now, you know, that's not much fun just doing that all the time, but we'll do a much more, there's a general property coming our way, which is to show how the Laplace transform of t times another function, how that relates to the Laplace transform of the function f. So we'll be able to show that the Laplace transform of t times f is just minus the derivative dds of the transform of f. So using that general property, we'll be able to prove all of these transforms, the transform of t to the power n for any integer n. But maybe the one I wanted to show you now was the cosine one. So we'll consider how to take the Laplace transform of cosine of omega t. So that's the Greek letter omega there in front of the t. It's traditionally used for kind of frequency-like terms. And how am I going to do this? Well, I'm going to make use of the fact that I can write a cosine as a combination of exponentials. Was it e to the ix plus e to the minus ix, isn't that right? This is one of my blind spots, so I'll just look it up. Yeah. E to the ix plus e to the minus ix. So this is so cosine of omega t is going to be a half of e to the I omega t plus e to the minus I omega t. So how will this help me to get the Laplace transform of cosine? Well, I can say now that the Laplace transform of cosine of omega t is equal to the Laplace transform of a half of all this, e to the I omega t plus e to the minus I omega t. At the end of the last lecture, we also proved, well, we didn't really prove it, we just observed it, really. This theorem, 2.1, the fact that the Laplace transform is a linear transformation. The Laplace transform of alpha f plus beta g is alpha times the Laplace transform of f plus beta times the Laplace transform of g. Did that have some big complicated proof or some long-winded proof? No, that was just an observation based on the fact that, well, because the Laplace transform is defined as an integral with the argument alpha f plus beta g is a factor in the integral, so then we just use the fact that integration was a linear operator. So an integral of a linear combination is exactly the linear combination of the individual integrals. And that gave us that result, theorem 2.1, straight away. But here I've got a linear combination, a half times this exponential plus a half times this one. So I can split it up as a half times the Laplace transform of e to the I omega t plus a half times the Laplace transform of e to the minus I omega t. But we've already done that. We've already done e to the minus at. It's 1 over s plus a. So I'm just going to make use of that. So e to the I omega t is going to be 1 over s. What do? You have minus a on the left, and that turns into a plus a. So here I've got a plus, so it's going to turn into a minus. So it's s minus I times omega. And then I've got a half of 1 over s plus I times omega. Now I'm trying to recover this answer here for cosine of omega t. I'm trying to show it's s over s squared plus omega squared. Well, that doesn't look like it at the moment. It should be this thing, s over s squared plus omega squared. This one that the mouse is pointing to just there. S over s squared plus omega squared. Well, how do we show that that is in fact the same as that? Well, here it's written as the sum of two functions at the moment, sum of two fractions at the moment. So we should collapse it together and write it as a single fraction, as it is here. So I want to see s minus omega times s plus I omega. And I've got a 1 over here, so I need to have a half of s plus I omega there, plus a half of s minus I omega there. It's just taking the two fractions and writing them over a common denominator. On the top, what do I have? I've got a half of s plus a half of s. So I've just got s on the top. And on the bottom, when you multiply it out, you've just got s squared minus I squared omega squared, which is, of course, what's I squared? I squared, remember, is minus 1. So s minus I squared omega squared is s plus omega squared. So as we expected from the table of Laplace transforms. Yeah, does that look good? So it won't surprise you to hear that sine of omega t, its transform can be found in a very similar way. So we find that in the same way using, of course, the fact that sine of omega t well, if cos of x d dx is minus sine of x, yeah, that's right. Sine of z is a half times I to the e minus I of z minus I e to the iz. So we can make use of that. So you've got sine of omega t is a half of I e to the minus I omega t minus I times e to the I omega t. And then just do the same trick again. Just say that the Laplace transform of sine of omega t is the Laplace transform of that. Use the linearity. Take the result about the exponential from the table and squash the two fractions together again and show that it comes out. And it will come out this time as omega over s squared plus omega squared. Okay. So I'll say finish this as an exercise. So, you know, if you get bored on Christmas Day after lunch or whatever, you know, just get this table out and just work your way down the list and prove all of these transforms using similar approaches, either using already, reusing the transforms you've already obtained, using various techniques for integration by parts, and so on. So we proved the linearity last time, and if you look there in example 2.3, this is an example of how we're going to use this property along with all the results from the table. And we'll need to be able to do that in quite a practice fashion when we're solving the differential equations, okay? Because solving the differential equations will require us to take the Laplace transforms of various functions. So just as an example, if you've got any kind of linear combination of the standard functions that are featured in the table, you can now write down what their transforms are, because you've got all the standard results in the table and you've got the principle of linearity. So for instance, the Laplace transform of 3t plus 4 times that exponential, e to the minus 2t, using the principle of linearity, the Laplace transform of that complex function should be 3 times the Laplace transform of t plus 4 times the Laplace transform of the exponential. And these two individual transforms, Laplace transform of t, from the table, that's 1 over s squared, and Laplace transform of e to the minus 2t, well, from the table, that's 1 over s plus 2. So that gives you the overall transform 3 over s squared plus 4 over s plus 2. So that kind of process that's in example 2.3, and which I illustrated slightly here with the cosine and the sine functions, using the linearity, using results from the table, we'll have to do that over and over again when we're solving the differential equations. Okay, so why don't we take a break for 10 minutes, the 10-minute break between lectures, and then we'll continue on. We'll continue on with this, and then Norman will arrive then later on. Okay, so we'll reconvene here. It's now 3:47. We'll reconvene at 7 minutes past 4. No, sorry, at 3:57. 3:57. 3 minutes to 4. If you got any more individual questions, feel free to come down.